Okay, sample problem 18.1 is about finding the order of a reaction from experimental data, which is given to us right there. And we have this generic uh, reaction where one reactant turns into one product. That reactant has a coefficient of little a, which doesn't mean anything in this problem. It gives us we didn't have to give us the rate law, but it did. We can figure it out here. I'm just going to rewrite that so I have a little bit more room to work with. All right, and the format is the rate is equal to the rate constant K times the concentration of the reactant. In this case, there's only one reactant and it has an order of X. We're going to solve for that right now. Okay, it's asking us to find the order with respect to A. And we'll also find the overall order, which is going to be the same thing. The overall order of the reaction is going to be the same because there's only one reactant. All right, otherwise you would have to add up the orders of each reactant. All right, which we'll see, I'm sure, in another example. All right, so to figure this out, you can pick any two trials. Let's just go one and two. All right, we're going to compare these trials. You could have picked 2 and 3, got the same answer, or for some reason, if you want to challenge, make it harder on yourself, you can compare 1 and 3. In any case, there's only one reactant. You can pick any two trials you want. Okay, so this scientist went into the lab 2 different times and performed 2 different trials or experiments. And the first trial and the second trial had this person added twice the concentration of A in the second trial. All right, so I'm going to put that right here where I see concentration. All right, it increased by a factor of 2. Okay, and when that person did that, increased the concentration by 2, the rate, when the reaction started right away, that initial rate was recorded and it went up by a factor of 4. So right here under rate, I'm going to put 4 because that's how much it changed by. All right, so now we're going to solve for that order, x. Okay, so 2 raised to what power is going to give you 4. All right, so the answer here is it's a second order reaction. Second order reaction with respect to A and second order overall, because that's the only reactant in here. Now just a careful note here, we can do this easily right now because we're just starting this topic, but you should know that experimental data does not come out so pretty like this. It was just designed that way. All right, so we can figure this out. These are not going to be whole numbers. These orders are not. And when that's the case, and when you can't just do this mentally in your head, you're going to have to whip out your calculator and do some logarithmic calculations, which hopefully we'll get to try before this is all over. So we've answered the question, but why not take this a step farther? So if you haven't done this already, pause your video and see if you can write the whole rate expression or the full rate law. So in other words, solve for K and let's write the full rate law. Okay, so hopefully you tried it. Let's get some more room. And all we're going to do here is pick any one of these trials, and it doesn't matter which one. Pick whatever has the easiest numbers you think are to work with. And I'll just pick trial number 2. Just notice, look at these odd scientific notation formats, huh? All right, but that's okay. All right, I'm going to use trial 2 just because I want to, and you can try it. You'll get the same answer no matter. Maybe you should try a different trial and see if we get the same thing. All right, so I'm going to plug in where I see the rate, right, which is right there. I'm going to plug that in where I see the word rate. So that's 12 times 10 to the negative 4. The unit here is moles per liter is molar. So it's molar per second. I'm going to write that seconds to the negative 1 because it'll be easier to read. And this moles per liter is again molar. So units can get very tricky, so you want to keep good track of those. Okay, that's going to be equal to the rate constant K, which is what we're solving for, times the concentration of A is right there, is 0.10, and then that's going to be all. Hold on, don't forget your units. That's molar. Concentration is measured in moles per liter. So that's it. That's it. There's only one reactant. All right, let's we could have rearranged this equation before we did all this. Maybe saved a little bit of time, but too late. All right, let's isolate K by dividing both sides by everything else. I'm gonna get rid of this parentheses. No, I'm not. I'm just gonna keep it there. All right, and do the same thing on the other side. Now here I'm gonna get rid of the parentheses because, all right, what? I might confuse some people. I'll just keep it there. All right. Let's wipe those out. That's the whole point of that. Isolate K. Now watch this. I'm going to have to write this a little differently. I'm gonna rewrite this. Right. So this is also equal to 0. I'm gonna square the quantity. That's 0.01. I'm going to square the unit, that's what you get. All right, so notice one of these molars are going to cancel out with one of these. Okay, so I'm just going to get rid of this there. All right, and what are we left with? Okay, well, dividing by 0.01 is the same thing as multiplying by 100 because you move that over that way twice, and you're going to all right, do the same thing on the top. Okay, so the answer is going to be pick a different color. No, let's just keep the same color. All right, so the answer, the K, little k, is going to equal to 0, 0. Just move the decimal over because I did the same thing on the denominator. All right, use your calculator if you need to. Times 10 to the negative 4. And the unit we're left with is molar. Okay, that molar is on the bottom, so we'll just molar to the negative 1 times seconds to the negative 1. Now we need to rewrite the scientific notation for sure. 1, 2, 3. We need to move the decimal over there. All right, so it's going to be 1.2 sig figs times 10 to the negative 1 because we increased the exponent by 3, right? Negative 1. Molar to negative 1, seconds to negative 1. That's our final. Oh, hold on. That's K. So let's plug that back into our rate law. All right, wow, we're almost done. So the rate law is going to be written equal to 1.2 times 10 to the negative 1, molar to the negative 1, seconds to the negative 1, times the concentration of A. And if you recall, that's a second order reaction. There's our rate law for this hypothetical thingamajigger.